Again, welcome to Calculus. This is Functions. This is our Unit 1, Lecture number 7. So our main objective is to go through decomposition of a function, also composition of a function. We are going to use the vertical line test to determine whether or not a graph represents a function. Also, we're going to recognize and apply the difference quotient. So first, we start with an example 1, recognizing the parts of a function. So given a function f at x equal to x squared plus 6x plus 8, we are going to rewrite f at x as a sum of two functions, one of which is linear. So here we can have two functions. Let's represent x squared as g at x, then 6x plus 8 as h at x. So here we say h at x equal to x squared, then g at x equal to 6x plus 8. So 6x plus 8 will be a linear function because the variable highest exponent is 1. So then we can say f at x is h at x plus g at x, because h at x is x squared plus g at x, which is 6x plus 8. Now the function g at x is called a linear part of f at x, and h at x is called the quadratic part. When the highest exponent is 2, we get a form of a function which is a quadratic form, parabola. And when the highest degree of the variable is 1, then we get a straight line, a linear function. So new functions from old. Here we say it is often useful and also simpler to write f equal to h plus g. Again, f equal to h plus g, instead of f at x equal to h at x plus g at x. In some texts, one says f at x equal to h plus g at x, but we will avoid this notation. The notation h plus g denotes a new function formed by addition. Also, it is not an addition of numbers. So we can sometimes write h plus g, or h multiplied by g, or h divided by g, or h minus g, instead of saying h at x plus g at x, h at s times g at x. So for a new function, will be formed from the functions, again, h and g. So let's see the next example, which is decomposition of a function. Now here they say we should find a decomposition of a function f at x into two simpler functions, g at x and h at x. We know decomposition means we have a big unit and we have to break it into smaller parts. So here we have a function f at x, and we are going to break it into smaller part of g at s and h at s. So defining new functions g and h, and express f in terms of g and h. So we have a function f at x equal to 1 minus 3x plus 16 square root of x. So the solution here, we can say h at x equal to 1 minus 3s, and g at x equal to 16 square root of x. So then we know that f at x equal to g at x plus h at x. B, we're going to do the same thing, decomposition of a function. This time we have a quotient, 3x plus 20 over 2 plus 13x plus 6x squared. So the solution, we can say h at x is 3x plus 2, g at x is the denominator, 2 plus 13x plus 6x squared. So again, the whole concept is f at x is a one unit, one function. We decompose it into two functions as h at x and g at x. So in order to get f at x, then I need to divide h at x by g at x. So we say f at x equal to h at x divided by g at x. Let's see the next example, f at x equal to 2x minus 1 times square root of x. So again, we are doing decomposition. We can break this function into two. We can represent 2x minus 1 as one function, then square root of x as a second function. So we say h at x equal to 2x minus 1, then g at x equal to square root of x. So f at x is equal to h at x times g at x. Now, operations with functions. Let's look at this example. We have f at x equal to s squared plus 6s plus 8, then g at x equal to s squared minus 4. So when we said operation, we mean the arithmetic operations. If I have two functions, I can add them together, I can find the difference of them, or I can divide, or I can multiply. So our first example here is we are looking for h at x, which is equal to f at x plus g at x. So f at x is given to us to be s squared plus 6s plus 8. G at x is given to us to be s squared minus 4. So we are going to add the two together. So here we get s squared plus 6s plus 8 plus s squared minus 4. So when we combine the like term, s squared will give me 2s squared. Then 6s is only 1. Then 8 minus 4 will give me 4. So this is addition of the two functions given to us, f at x and g at x. Now we are going to do a difference, f at x minus g at x. So the solution means we're going to subtract g at x from f at x. We are going to remove the parentheses and change the sign of the second fraction or the second parenthesis into minus s squared plus 4. And when we combine, we get 6x plus 12, because we are going to get minus s squared and we have plus s squared, so they'll cancel each other. Then we have plus 6x by itself. Then we have plus 8 and plus 4, which will give me plus 12. We can also do multiplication. So we are going to multiply the two functions f at x and g at x. So we multiply s squared with s squared minus 4, 6x with s squared minus 4. Then we multiply 8 with s squared minus 4 also. Then we remove the parentheses. So s squared times s squared will give us s to the power 4. Then 6s times s squared will give us 6s cubed. Then we have 8 times negative 4 will give me negative 32. Then we also have 8 times s squared, which will give me 8s squared. Then we have also 6x squared. So we combine it, and this is what we have after we combine the like terms. So multiply all the each term with the second parenthesis, also each term. Okay, so next is division. We have our f at x is s squared plus 6s plus 8 divided by s squared minus 4. So here we factorize the top, we get trinomial, we get s plus 4 and s plus 2. First we factorize s squared, which gives us s and x. Then find two numbers. When you multiply, you get 8. When you combine, you get 6s. And that will be 4 and 2. 4 times 2 is 8. Everything is positive, so we get plus 4 plus 2. Then the denominator is a difference of two squares. 4 is the same as 2 squares. So s squared minus 2 squared will give me s minus 2 times s plus 2. Then here we can see that s plus 2 will cancel each other. So the final answer will be s plus 4 divided by s minus 2. So we finish with decomposition. Now we go to composition of functions. So it's opposite. Decomposition means we have a big unit. We want to break it into two or more. Composition means we have smaller units and we want to combine them. Let's say we have two functions, we want to combine them as one function. So here we said that if f and g are two functions, then the composite function of f and g is defined to be f g at x will give me f at g at x, and the domain of f and g is that part of domain of g for which f composite g is defined. So let's do an example. Hopefully the example will help us understand. So if I have f at x equal to square root of x minus 1 and g at x equal to x squared plus 2, and they say we should find the composite of f at g at x, it means I'm going to write down f at x function first, which is square root of x minus 1. Now, anywhere I see x, I'm going to substitute with the g at x function. So here we're going to get square root of x squared plus 2 minus 1. Because we see x, we substitute with x squared plus 2. Now the opposite, if they say we should find the composite of the function g at f at x, I'll write down x squared plus 2 first, the g. Then anywhere I see s, I'm going to substitute with f at s function, which is square root of s minus 1. So let's find this. We can say we have our square root. Instead of writing x, I substitute with x squared plus 2. So that will be g at x, then minus 1. So this will give me x squared plus 2 minus 1. And finally, our answer will be square root of x squared plus 1. Now let's do the opposite. Now we are finding composite of g f at x. So we write down the g first. So we have g, then f at x. So which means that our g is x squared plus 2. So we wrote f at x squared plus 2, we substitute. And we get square root of x minus 1 squared plus 2. Because f at x is square root of x minus 1. And anywhere I see x in my g function, I will substitute with the f at x function. So square root and x squared will cancel each other. So we get x minus 1 plus 2. And the final answer will be s plus 1. So operations with functions. Here they say we should note that f composite g is not the same as g composite f. As we can see there, we saw our two previous examples. Their solutions are different. Now, if I have a function f at x equal to 2x squared plus x, and g at x equal to 3x, now they say we should find the composite of f h at x. So this means I'm going to write the f at x function first, which is 2x squared plus x. Now, anywhere I see h at x function, which is 3x, I'm going to substitute x with 3x. So the solution will be, first we'll write down 2x squared plus x. Now, anywhere I see x, I'm going to substitute with 3x. So this will be 3x squared, then plus 3x, because we have x, we turn to 3x. So here we get 9x squared, and 9x squared times 2 will give me 18x squared plus 3x. So let's do the opposite. This time we are looking for the composite of h f at x. So I'm going to write down the h function first, which we can say it was 3x. So we write 3 f at x. Then we substitute f at x, which is 2x squared plus x. So finally we get 3 times 2 is 6, x squared plus 3 times 1 is 3, and times x. So our solution will be 3x squared plus 6x squared plus 3x. So here we say in each case, we should identify two functions, h at x and g at x, so that the given function f at x can be expressed as f at s equal to g composite h at x. So we have a is f at s equal to 3s plus 1 square root. So the solution here will be h at x is what, 3x plus 1. Then g at x will be square root of x. So again, in each case, identify two functions, h at s and g at s, so that the given function f at s can be expressed as g at h at x. That's the composite g at h at x. And now we have f at s to be square root of 3s plus 1. So here we let h at x become 3s plus 1. Then g at s will be square root of x. Then we have f at s equal to g, composite g at h at x, which will give me g at 3s plus 1. And finally, we get square root of 3s plus 1, because g at s is square root of x. Okay, so another example, composite function, f at s equal to 3s minus 5 raised to the power 5. So the solution here, we have h at s equal to s minus 5 and g at s equal to 3s to the power 5. So f at x equal to g h at x will give me g at x minus 5, because h at x is x minus 5, which will give again g also at x is 3s to the power 5. So first we write down our g, which is 3x to the power 5. Then anywhere we see s, we substitute with h at x, will give me s minus 5. So C, we have f at x equal to 10 to the power 3s plus 1. So the solution here will be h at x is equal to 3s plus 1. Then g at s will give us 10 to the power x. So f at s will equal to g composite h at x, which will give me g 3s plus 1. And we know g is 10 and raised to the power x. So x will give me 3s plus 1. So the answer will be 10 to the power 3x plus 1. Now we have f at s equal to square root of 3s plus 1. This time we are going to calculate f at 1 by first calculating h at 1, then g h at 1, which is equal to f at x. So we have f at s equal to square root of 3s plus 1. So anywhere we see x, we substitute with 1. So we get 3, 1, and times plus 1. And that will give us 4. Now with f at 1, we give a g h at 1. So we know h at 1 is 4, so we get g at 4. Which again, f at s square root, so it will be square root of 4, which will give us 2. Then we have f at s equal to 3s minus 5 to the power 5. H at 1 will be 1 minus 5 equal to negative 4. Because s is 1. So, and f at 1 equal to g h at 1, which will give me h g at negative 4. And then 3 times negative 4 to the power 5, which is what we have here. Then 10 to the power 3s plus 1. H at 1 will give me 3, 1 plus 1, which is 4. Then g at h at 1 will give me g at 4, which is 10 to the power 4, roughly 10,000. So next will be the difference quotient. Here they say we should note that the quotient expressed below will occur repeatedly in later session, and we wish to emphasize that each quotient are slopes. So m is dy dx, dy will be y2 minus y1 over s2 minus s1, which is the same as using a function f at s2 minus f at s1 divided by s2 minus x1. So we have an example here. We have f at s equal to 8 minus s squared. Now they say we should calculate, simplify, interpret the following expression. F at 5 minus f at 3 divided by 5 minus 3. So the first thing we have f at 5 minus f at 3 divided by 5 minus 3. And we know, again, our f at s is 8 minus s squared. So we get 8 minus f at 5 squared. Minus 8 minus is 3, so 3 squared. And 5 minus 3 is 2. So at the end, we're going to have negative 16 by 2, which will give us negative 8. So next, we are going to calculate dy dx. If a and f at a and a plus h with f at a plus h are 2 points on the graph of f at x. So solution of dy will be y2 minus y1. So here we have y2 to be f at a plus h minus f at a, which we can see here. Y1 is f at a, y2 will be f at a plus h. So we substitute the values, then we combine, remove the parentheses, and our final answer will be minus 2ah minus h squared. And the s will be s2 minus s1. S1 is a, s2 is a plus h. So we get a plus h minus h, and our answer will be h. So next example, we are looking for the slope, which is dy dx. So f at a plus h minus f at a divided by h for the 2 points in part B. Part B, we find the dy separately and dx separately. The slope will be dy dx, and that's what we're doing. So we substitute the values that we had for dy, which is f at a plus h minus f at a, which is minus 2ah minus h squared divided by h. H is common, so we can cancel h out, and our final answer will be minus 2a minus h. So this will be the conclusion of our lectures. Again, these lectures, we continue with our functions, and we've went through the concept of decomposing function and also composition of functions and how to evaluate them. So again, wish everybody the best, and thank you again.